just get started. Today we have Dr. Shankar Bhamidi from the Department of Statistics and Operations Research at the University of North Carolina, Chapel Hill. And Dr. Bhamidi's research interest is mostly on stochastic processes and
I think that this
random
would be
networks.
timely, so you can get theoretical. So I think some of the things.
Please mute yourself for the audience. Okay, so Dr. Bhamidi's research interest is on stochastic processes and random networks. So today he will tell us something on the long-range dependence in evolving networks. Please go ahead, Dr. Bhamidi.
Okay, again, thank you very much for the invitation. So just two things before I dive in. So I think one of the emails, I think perhaps it was from Judith, she'd emailed about, I think maybe the chair had suggested that the first few slides, a few minutes should be hopefully understandable for everyone. And so the natural, logical suggestion after this is, I was thinking, can I make a talk which is maybe almost completely understandable for people in our audience, or people who have at least some basic background in statistics and probability. So this is what I've tried to do. So there won't be, typical talks, I think I jokingly say they tend to be what I call shock and awe type of talks. My stuff is the greatest since sliced bread or something. So unfortunately, this won't be that sort of talk. So I apologize in advance if this is what you're looking for. And the second, maybe the key message of the talk that I want to convey is, I think all of us know that the networks play a big role in our lives, whether this be in how infection spreads on contact networks or how misinformation spreads on social networks, influencing how people behave. And so this, in terms of research for our particular community, this is very good. There are lots of people who are thinking about problems in this area. And the key message I want to convey is, one, networks inherently are very complicated. One can think of very simple models which give very complicated outcomes. And unless one actually does the math, one cannot understand what's happening. And so it's very important for our community to do this. Your colleague, Tiandong Wang, she's done some really cool work in her career already. And so there are lots of open problems and lots of opportunities for us. Okay, so that's the key message. Okay, so I'll start with some just a bit of structure of the actual talk. Then I'll mainly discuss two topics, seed detection, dynamic networks, and then change point detection. And then if I have time, it's buy two, get two free sort of deal. If I actually have time, which I don't think I will, I'll maybe mention some more stuff about epidemic models and Mcmc algorithms for networks. Okay, so terminology, most of you probably are familiar with this, but so when I say a graph, I just mean a bunch of vertices. Think of these as people connected by edges, representing some sort of interaction between individuals. And when I say network, typically these are graphs with potentially some sort of context-dependent structure or graph with benefits. So both of these are things that my advisor coined. So for example, you start with a graph and then maybe you have weights on the edges, or you start with a graph and each vertex has some label telling you its age in the system. So this is a graph and a network. So for the structure of the talk, so I'm going to be telling you a few problems. For each problem, what I'm going to do is I'm going to have one slide trying to tell you about the motivation in words. So a very general description. And I would say this is the only important bit of that particular problem. And then I will describe my specific or our specific contributions. Much of the stuff here is done with collaborators, my colleagues or students. And so, this could be potentially irrelevant. You might not be particularly interested in the model we are considering, et cetera, et cetera. So there may be at most 2 or 3 slides which I would consider important, and the rest are, you can look up papers. I'm happy to talk to you, et cetera. Okay, so the first problem is seed detection in evolving networks. And again, at a high level, the goal is if there's, say, some sort of infection spreading from some sort of individual, let's call it patient 0, And at some point in time, you observe the graph and you know who's infected, but you don't know when they got infected. Can you detect patient zero from this sort of data? So our motivation in words, so suppose you have some sort of dynamic network and you start with a single vertex, or you could even start with a seed graph, like a bunch of individuals connected in some fashion. But let's just think about a single node, and let's call this, say, patient zero, for example. And then what happens is this network evolves over time. New people come into the system, connect to previously existing vertices in the system. And you observe the network when it's of some super large size. Let's say when you have 1 million nodes or 1 billion nodes in the system, and you don't have any temporal information. You only have topological information. For example, the adjacency matrix, who is connected to whom. And now suppose you have a fixed budget, let's say k equals 30, or let's even make it more extreme. Suppose you have a budget of 3. So you have 3 people in the network. You have a budget of 3. And so what the goal then is, you want to output 3 vertices from your network such that with high probability, the seed, the person who started this entire network, is in your outputted set of 3 vertices with high probability. Okay, so that's the basic goal. You have a 1 million node network. You just want 3 people such that with high probability, one of them was the person who started the actual network. So let me tell you about now the specific model that we're going to be considering. So start with some sort of attachment function f. And so what this attachment function f measures is, at any given time, if you have a vertex of some degree, then f of that degree measures how attractive this person looks for new people entering the system and wanting to form connections to this person. Okay, and so at each stage, a new vertex enters the system and connects to one pre-existing vertex with probability proportional to f of the degree of that vertex. And so if the f, for example, if that's monotonically increasing, then that means the more degree a person has, the more friends they have currently, the more popular they look for new people entering the system. And at any given time, tau n will represent the network of size n. And when I say size, I mean when there are n people in the network. So let's just consider a simple example. So suppose f is equal to 1. So what this means is identically equal to 1. This attachment function is equal to 1. What this means is the degree plays no role in the evolution of the system, and people just randomly, so a new vertex comes in. Let's say this is vertex 3 that comes into the system. I'm just going to put 1 and 2. Then vertex 3 comes into the system and connects to one of these uniformly at random. Let's say decided to connect to vertex 1. Then vertex 4 comes in the system, connects to these 3 people uniformly at random. Let's say here, vertex 5 comes in. Let's say connects here, 6, here, 7. Once again, decides to connect to 1, etc. Okay, so people come in and uniformly at random, they connect to someone in the network. The degree of people have no relevance in how this network is evolving. So this network might appear to be unrealistic as a model for an evolving social network, but there are lots of reasons for studying it in the world of computer science. It's a very important concept called a random recursive tree, shows up in many areas like sorting algorithms, etc. But this is one specific example of a network. And so just in terms of simulation, so I simulated this when maybe there are 3,000, I think, when n is equal to 3,000, there are 3,000 vertices in the system. And I'm going to magnify this just a little bit. And so the people who started, so this is vertex 1, this is vertex 2, and this is vertex 3. These are the 3 people who actually, the first 3 people who started the system. But now the goal is, forget about 3,000. Suppose I had 1 million, not just 3,000. Suppose I had 1 million node network. And now it's hard to plot it. But suppose I gave you just the adjacency matrix of the graph, and I asked you, can you find, at least with high probability, the first person, or output a set of 3 people, so that with high probability, patient 0, vertex 1, is in that outputted set of 3 people. So can you do this? So that's the basic question. And maybe in words, the perhaps surprising fact is, yes, you can. Of course, this 3 would not be 3. It might depend on your probability of recovery, but it will be some size that I can tell you how much budget you need. and this budget will not increase with the size of the network. So it doesn't matter if it's a million, a billion, etc. I can tell you, if your error tolerance is so much, how many vertices do you have to output, and I'll give you an algorithm so that you're able to find the seed. Okay, and to give you another example, this is called preferential attachment network. So here, the function f of k is equal to k. So with you attach to a person with probability proportional to their current degree. And this model, so Tian-Dong knows this very well. She's done a lot of work on this. But this model has been known for a long time in our community, all the way to Yule in the 1920s, but it came to the attention of people in the network community in around 1999, 2000, because of the work of Barbasi and Albert, who formulated this as a simple model for how, say, the web graph evolves. And so just to give you an example, let's say, so this is vertex 1, vertex 2 comes in, it has no one else to connect to but now vertex 3 comes in, and now the weights of the individuals here, both of them have degree 1, so both of them have weight 1. So let's say vertex 3 decides to connect to vertex 1. Now this vertex, the weight gets updated to 2, and so now when vertex 4 comes in, it has a higher chance of connecting to vertex 1. Let's say it decides to do this, and so then the weights get updated. So this now has weight 3, this has weight 1, this has weight 1, and a new vertex comes in and decides to connect. Okay, and so this is called preferential attachment models. And so once again, here's a simulation now on, I think, around 5,000 vertices. And here, this should not be surprising that maybe one might be able to find the root or the people who started this graph. So all the red vertices are here, and they're also pretty close, if not the maximal degree vertices, they're pretty close to the maximal degree. So in this sort of network, there's a very simple algorithm, which is try to find the people with the most number of friends, and the people who started this system are probably somewhere near them. Okay, so bottom line, in some cases, one might imagine it's easy to find the root. In other cases, it's not easy. It might not be at first sight easy to find the root. Okay, so so this is what I'm going to tell you about. So when I showed you this picture, I said the natural algorithm is find the vertices with maximum degree. So essentially what I'm doing is for each vertex in the graph, I'm coming up with some functional that measures its centrality. In this case, it's degree. And then I'm outputting the maximal or minimal vertices with that centrality measure. So this is the most natural class of seed detection algorithms. So for every vertex who obtains some measure of centrality, okay, so phi of u, this is some measure of how central this is in the network. We could do degree centrality. This works in some cases, but for example, in the random recursive tree case, one can actually show this will not work. And I'm going to tell you about another measure called centroid centrality. But once you've decided on your measure of centrality, suppose someone tells you, I'm giving you a budget like 3 or 30. Then what you can do is once you've decided on your centrality measure, you can output the top k vertices. And here the top could be largest or smallest k vertices based on the centrality measure. And we're going to say that this sort of algorithm has error tolerance epsilon if the chance that your seed, and so when I say seed, I mean vertex 1, the vertex that started this whole system, the probability that it belongs to your outputted set, the chance of this is greater than or equal to 1 minus epsilon for all large size systems. For any large size system, it's greater than or equal to 1 minus epsilon. Okay, then if I can do this, then I say that I've achieved an error epsilon tolerance. Questions? Okay, so so the fundamental questions here are, so for a given error tolerance, epsilon, for example, 0.01, can I select this budget k, which is independent of the size of the network? And this is at first sight not obvious. If I have a billion node network, maybe I need a much larger outputted set to have some hope of recovering the seed as compared to, let's say, a 1,000 size network. Okay, so this first question is at first sight not obvious that one can do this. And even if you can do this, then the natural question is, how does this budget depend on epsilon? So do you need, an outputted set of size 1 over epsilon or order 1 over epsilon, is that enough? Or do you need an outputted set of size 1 over epsilon to the power 100 or something much larger, etc.? So how does this depend on epsilon? How does this depend on your model of interest, your model? And I should say your generating mechanism, network generating mechanism. Okay, so these are the questions that we are interested in thinking about. So before telling you the main facts here, so I'll tell you about one measure of centrality that works in most known models. And this is called the Jordan centrality. And so this works in the context of trees. And so the basic idea is the following. So suppose I fix a candidate vertex B, for example, this one. And I'm trying here in my house, I'm trying to think, is it possible that the network started from this vertex? So was this patient 0? So to measure the likelihood of something like this, what I can do is the following. So this vertex has 3 descendant subtrees. So if this vertex started the actual network, there are 3 descendant subtrees over here: the green, the purple, and the yellow subtrees. So here, this should have chosen a better color here. This has size 3. This has size, forget now, something like 9 or something, and this has size 1. Okay, so each of these subtrees have their own sizes. And so my score for this vertex is the size of the largest subtree, in this case, 9. Okay, so let's just take another example. So let's say this is not the vertex. Let's say this is my vertex B. I'm trying to judge whether the likelihood of this vertex having started the network. Then this vertex has only 1 subtree hanging off it. And I think the size of this subtree is 13. So in this case, this is 13. So the basic idea is vertices that are at the fringe of your network, that are really on the border, the stuff that is hanging off them will be really large. So this vertex here has a large. So large, let me just write this in words. Large means at the fringe of the network, at the outer boundary. So small means good, large means bad. So this is one notion of centrality. And so the basic algorithm is measure each vertex's centrality using this notion. This is called the Jordan or centroid centrality, and output the vertices with the smallest. So someone gives you a budget, let's say 30, then you output the vertices with the smallest K Jordan centrality measure. Okay, and so that's the algorithm. So someone tells you 30, output the 30 vertices with smallest K centrality measures. So this is the algorithm. And so then the basic question is, what can you say about this? So if I give you a trillion node network that was generated using this generating mechanism, can you find the root with high probability? Or will this algorithm find the root with high probability? And so with my colleague, Sayan Banerjee, what we managed to do was we managed to derive sufficiency bounds. So in terms of, there are too many details here, ignore this. All I'm going to say is, in terms of assumptions on your attachment, in terms of your assumptions on your attachment function F, namely the probability generating mechanism, we can tell you that if you choose a budget, so someone tells you that their error tolerance is some epsilon, like 0.01, you plug this into this formula, and that tells you that if you output the vertices with the K smallest centroid measures, where K is given by this formula, then with probability at least 1 minus epsilon, doesn't matter how large your network is, your seed will belong to this outputted set. Okay, and so there are sufficiency bounds. There are also necessary bounds. That is, you need a budget which is at least so large, depending upon your attachment function. And so there are too many details on these slides. So let me just show you what this means for specific models. So for example, for the uniform attachment case, the random recursive tree, where people come in and randomly connect to one of their existing neighbors, one of the existing vertices in the network. Essentially, if you output 1 over epsilon many vertices, so the centroid, the central vertices as measured by centroid centrality and order 1 over epsilon, you're going to be able to find the root with high probability. If you have a preferential attachment, then you need an order 1 over epsilon squared many vertices to find the seed of the network. Now, if you change the model just a little bit, and so this is why the title of the talk said long range dependence. So what happens at the beginning or the initial part of the network or the system very sensitively depends on the model parameters. So for example, instead of f of k equals k, if I do f of k equals k plus beta, so preferential attachment plus a small offset term beta, then I need, this is also reflected in the amount of budget I need. Then I need a budget of 1 over epsilon to the 2 plus beta or 1 plus beta, etc. Okay, so in specific examples, so there are general necessary and sufficient bounds. And then for specific examples, these give you almost tight necessary and sufficient bounds on how many vertices you need to output, irrespective of the size of the network, to get the initial seed. Okay, so this is the basic punchline for seed detection. So I'm going to be moving to my next topic, but any questions over here? Okay. Okay, so the next topic is, in the context of networks, is change point detection. And so we as humans, I think we are, people say that humans are pattern recognition animals. And in particular, we are very sensitive to changes in our environment. And so change point detection is a beautiful field at the intersection of applied probability and statistics. And I think all of us are aware of, say, univariate time series. So for example, I was looking up for this talk, the US life expectancy, and plotting this as a time series. And you can see at various points in time in the past, there have been huge drops in the life expectancy, the 1918 pandemic, World War II, and then most recently now, because of the COVID epidemic, there's a significant drop in life expectancy. We'll see, how this continues. So change point detection, trying to look at time series and trying to figure out if changes in this time series are actually, there is some reason for there being a change, or it's just some sort of either artifact of randomness or measurement, etc. This is a thriving area. Now, in the context of network time series, suppose you have some temporal network data. So this could be, for example, adjacency matrix, an adjacency matrix of a temporal network. So you have a network that's evolving over time, and you observe its adjacency matrix at all periods in time, or maybe only a subsample of time points. Or perhaps you don't get to observe the network itself, but you observe some sort of time series at each node in the network. So for example, neuroscience, you get signals from different regions in the brain, but but people believe that there's some sort of underlying network connectivity that drives how these time series sort of evolve in a coherent manner. So suppose you have network time series in these sorts of fashion. And now suppose the network experiences some sort of shock at some point in time, okay, an abrupt shock in the system. So the basic questions that we are interested in is, can we detect this change point if you observe this network time series? Can you observe this based on your measurements or what you observe? And perhaps as importantly, this shock to the system, what structural properties of the system does it actually change? Does the degree distribution change? Do things like degree exponents of the system change, etc.? So these are our motivation in words. So now so this is the only important slide. The rest is sort of more details. So the model that I'm going to consider is the same previous model, where one has some sort of attachment function f that drives the evolution of the network. So the model without change point is at each stage a new vertex enters the system and connects to one pre-existing vertex with probability proportional to f of the degree of that vertex. And once again, tau n is the network at time n. And so, as I said, this preferential attachment model, for example, people have been very interested in thinking about and working on. And one of the reasons that people really were interested in working on this is it was one of the first models which gave a simple generative mechanism to explain the emergence of heavy tail degree distribution. So what does that mean? So if you look at the number of vertices of degree k in your network, so this depends at time n. So when the network has n vertices, then this nk or n converges to pk. So another way of saying this is if you look at the degree distribution of your graph, it converges to some sort of proper probability mass function, pk, where this pk, this limit degree distribution has a heavy tail degree exponent. So pk scales like c over k to the alpha plus 3. Once again, alpha is this parameter here. You're connecting with probably proportional degree plus alpha. I'm just trying to give you some motivation as to why people look at these networks, and then I'm going to, this is like an active learning seminar. I'm going to ask you, the audience, a particular question. So anyway, so the degree exponent of this this model is alpha plus 3, and the maximum degree of this network scales like 1 over n to the alpha plus 2. Okay, so these are all known facts about this particular network model. So now let me just change the model a little bit. So suppose I fix parameter gamma in the interval 0 to 1, and I have a network change point setting. So up to time, so from time 1 to n gamma, the network uses this function f of k, which is k plus alpha in its evolution. Now from time n gamma plus 1 all the way to n, the network uses a different function g. So g of k is equal to k plus beta, and let's just assume that alpha is not equal to beta. That's the only assumption I'm going to make. And so for another period in time, it uses a different parameter, beta, in its evolution. And so now we come to the audience question here. So once again, recall that suppose the network, so I'm rescaling time to be between 0 to 1. And so what this means is, so 0 corresponds to when the network had one vertex. Gamma means it's of size n gamma. So from time 1 to n gamma, or 0 to gamma, I used one function f in how the network evolved. And then from time n gamma, so when the network became size n gamma all the way to n, I used a different function g. And once again, recall that if there was no change point, then if I just ran the system for the entire time f using this function f, my degree exponent is alpha plus 3, known results. If I use this function g for the entire time period, no change point, the degree exponent is beta plus 3. Okay, so now my question to you is, so any guesses on what the degree exponent should be in this new change point network model? Okay, so once again, so what I'm saying is, so let's assume that if you look at the number of vertices of degree k, this converges to some sort of pk. It depends on my functions, f and g. Then pk, suppose I tell you that pk f comma g, this is some k to the, I should have used a different function here. It has a heavy tail degree exponent, which should in principle depend on alpha and beta. So any guesses, maybe for everyone other than Tiandong, so any guesses on what this function could be, this dependence on alpha and beta? And I'm sorry, it should of course also depend on gamma, where the change point happened. So there are no wrong answers. This is how research starts. This is how we started our research, because this was what we were trying to understand, because then we wanted to use this to propose a change point detection estimator, blah, blah, blah. So we were trying to guess this is where we started. So once again, without change point, alpha plus 3, if you used f, beta plus 3, if you use g. Now, for some period, you use f, then after some other period, you use g. So my question to you is, any guesses for what this should be? Alpha beta gamma is equal to, what is the degree exponent?
Maybe weighted average between.
Very good. Yeah, excellent. Yeah, this was exactly our guess as well. A natural guess, for example, could be, I don't know, let's do gamma times alpha plus 3 plus 1 minus gamma times beta plus 3, this would be a very natural guess, or maybe, there's a more complicated dependence on gamma. Okay, so excellent. So this is where this is what we had guessed as well. And so maybe I'm just going to tell you the punchline of the basic theorem. So it doesn't matter what gamma is. Gamma could be 0.01. Gamma could be 0.000001. It doesn't matter what it is. This initializer function always wins. So I've purposely made this picture to make it look like your function f has just a very small time interval, and then the function g has a long time interval to affect the system. But it doesn't matter how large this is, as long as your function f has some non-trivial interval to influence the system. This is the function that determines structural properties of the network. So going back here, this was our natural guess as well, but the correct answer, it turns out to be, doesn't matter what gamma is, as long as gamma is positive, it's always equal to alpha plus 3. Beta plays no role in the asymptotic description of the network. Okay, so now maybe, so this was just, I just wanted to use this as an example. Let me just briefly tell you about the actual model itself. So one didn't need it to be this linear preferential attachment. So you have from time 1 to n gamma, the network uses some function f, and from time n gamma to n, it uses a different function g. These functions have to satisfy some sort of regularity properties, but they don't have to be linear, for example. And so once again, this is what the network change point setting looks like up to time 0 to gamma in normalized time units. I use f. And so at any time t represents when the network is of size nt. And from time n gamma to 1, it uses a different function g. And our goal now is, suppose, let's say you're in a grade setting where you observe the entire, all the network time slices. Can you estimate gamma? And things like estimating the degree exponent, like Hill estimator, something that Professor Tiandong Wang's PhD advisor, Professor Resnick, he has fantastic results on Hill estimators, estimating heavy-tailed degree exponents, heavy-tailed exponents. So what we have shown is those sorts of things won't work because there's no change in the degree exponent. But but that's the basic question. Can we estimate the change point gamma from these network time slice observations? And once again, no information about f and g, let's say. So we're in the non-parametric regime. So with Professor Banerjee in my department and a student, Ian Carmichael, what we showed is that you can probabilistically, mathematically, you can understand what happens to things like degree distributions. And although the degree exponent doesn't change, the degree distribution does change. So from the model with change point, without change point, there is a change in the actual limiting degree distribution. And so using this, so the actual technical description of this is very reasonably complicated. But what it leads to is the following. For general functions f and g, irrespective of how small gamma is, this initializer function f always wins. So for example, if your degree exponent with f without change point was something delta, then so is the model with change point. Okay, and again, doesn't matter how small gamma is. So if your degree distribution without change point had, for example, an exponential tail, then your degree distribution with change point. So for example, suppose your model was f is equal to 1 from time 1 to a very long period, or a very short period, I'm sorry. So from time 0 to 0.01, you use f is equal to 1, which means people come into the system and randomly attach to someone in the system. And then from time 0.01 all the way up to time 1, you use a preferential attachment. So g of k is equal to k. Should be a bit more clear here. G of k is equal to k. Then what you end up getting in this sort of model is you don't get a model with heavy-tailed degree distribution. You get a model, or the limiting degree distribution has exponential tails. So although for most of the time you ran a preferential attachment model, If the initial segment, you ran it using something else, like random attachment, the eventual model, you end up getting an exponential tails and not heavy tail degree distribution. So that's the first thing that this theorem gives you. But the second thing it gives you is, so what you can do is, because there is a change in the degree distribution, like properties of the degree distribution, what you can do is the following. So you observe your network when it's big, but not of size n. So observe the network when it's of size n or hn. And what we're going to do is we're going to look at the degree distribution as a functional that will tell us or alert us to the fact that there's a change point. So at when the network is not too large, we keep track, we write down what the degree distribution is. And then what we do is we measure the degree distribution after this time and compare it with the degree distribution at this time. And whenever there seems to be a big change in the degree distribution when compared to what it was at time n over hn, then you get alarmed and you say, oh, I think there's a change point. And then you say, that's my change point estimator. So what I've told you in words, this slide is saying this in more math language. So this is, you look at your degree distribution when your network is of size n over hn or at time hn over n. And at any given time t, you compare this with this degree distribution. So this is the distribution at time t, you compare it with what it was at time n over hn. And the first time when this becomes slightly large, so some notion of distance between this becomes slightly large, you get alarmed. So this is the first time this distance becomes slightly large, you get alarmed, and then you say, oh, I think there's a change point. And so then once again, using the math results that we derived, what you can do is you can show that the estimator is consistent. So as n goes to infinity in this general setting where you don't know f and g, but you do know that there's a change point, this estimator converges in probability to the true change point, to the true change point. But if you actually ask how well does this sort of estimator, and so I would like to emphasize that the main point of this talk is not a shock and awe type of talk, but the fact, just to tell you that there are lots of open problems in these areas. If you actually ask how well does an estimator like this do in actual simulations, then so this is a pretty large network simulation. So a network of eventual size 2000, and the change point was, I think, there was a change point. The change point was at the midpoint when the network is of size 100,000. And so over lots of simulations, so we start with a preferential attachment model and then become something called sublinear preferential attachment. So before change point, it's linear preferential attachment. After change point, it's sublinear preferential attachment. This red line is the true change point. And over lots of simulations, this blue bar is the change point detection estimator that we proposed over lots of simulations. And as you can see, even for a pretty large network of size 2000, although we can prove consistency, its actual performance is pretty poor. So, so lots of open problems. I can't spell problems here, but lots of open problems, and improving these sorts of estimators all completely open. Okay, so I have, I think, 5 more minutes, so maybe I will end with the final topic, which is completely unrelated to the previous 2 topics. But the goal again is to try to tell you that at the end of the day, although networks and network science is super important, one really has to do the math to understand these models. So the final topic is MCMC algorithms for network models. And so the motivation for something like this is the following. So one pipeline for analyzing network value data is the following. You posit some sort of parametric model for your data. You write down a likelihood function of the parameters given the data, and then you try to maximize the likelihood. Okay, obviously there are many more Bayesian reformulations of this, but this is one pipeline for many for many ways of analyzing network value data. And so this thing in the shaded block region, in many cases, writing down the likelihood function is intractable. So what one needs to do is you need to run a simulation algorithm to estimate the likelihood for each parameter value over some sort of grid. Okay, and then you do maximum likelihood. So bottom line, one has to run MCMC algorithms at the end of the day to try to get some notion of the likelihood before maximizing it. And so our motivation was to understand these MCMC algorithms. So trivially, one can show that if you run your algorithm long enough for time infinity, you will get the model that you're looking for. But how long do you need to run this in terms of getting close to the stationary distribution? And indirectly, it turns out that analyzing the MCMC algorithm actually gives you conceptual insight into the proposed model. So in a number of cases, it actually tells you that this model that someone came to your office with and said, I want to use this for my data, it tells you that that's the wrong model to use. Okay, so these are the two motivations, which I'll try to convey in 4 minutes. Okay, so the main model of interest is something called exponential random graph models. So these, at the risk of hyperbole, these are one of the main models in the world of political science and sociology. And so a very simple, one simple example is the following. So suppose you're looking at the space of all simple graphs, simple meaning there are no weights on edges and there are no self loops, etc. So this can be represented, any such network can be represented as an edge indicator configuration. So you're indicating 0 represents a particular edge being absent, 1 means that edge being present. And so it can be represented in this sort of fashion. And so people often posit a model of the following form. So probability of observing a particular configuration X is of the form e to the hx, where hx, this Hamiltonian term, has features that you think model your quantity of interest. So for example, in sociology, people believe transitivity is important. So if I'm connected to Tiandong and if I'm connected to Sid Resnick, then probably Tiandong and Sid Resnick might know each other. So there are more number of triangles in real world systems than just at random. So you put in a term that is the number of triangles in your configuration, and then you posit a model that looks like this. Probability of a configuration is e to this hx. Okay, and so this is why, or one reason why these are called exponential random graph models. And I'm sure there are people in the audience who know much more about things like the exponential family of models in statistics. And so the basic question we're going to be thinking about is, can you sample from these sorts of distributions efficiently? So the general model is the following. So a sociologist or political scientist, they come to my office and they tell me that a bunch of features, like G1 could be a triangle, G1 could be a triangle, G2 could be a square, I'm just making things up, etc. So they give me a bunch of graphs of some size L. So for example, I could stop here. And then they tell me that the model that they're looking for is of the following form. So hx is beta 0, the number of edges in your network, x, plus this sort of beta. So let me just give you an example for this specific setting here. So beta 0 times the number of edges in your graph, plus beta 1 times the number of triangles in your configuration x. Now the number of edges scale like n squared. The number of total number of triangles scales like n cubed. So to get a non-trivial model, you have to rescale things over n plus beta 2 times the number of squares in your configuration x. And this scales like n to the 4. So I need to scale this by n squared. Okay, so that would be my Hamiltonian. And then I come up with my actual model is Pnx is e to the hx. So in hopefully 1 or 2 minutes, I'll conclude. So this is my model. And the basic question is, can you simulate from this model efficiently? Okay, and so the main tool in town is Glauber dynamics, Gibbs sampling, etc. So basically, you set up a discrete time ergodic Markov chain whose stationary distribution is what you want. So in pictures, what you do is, if you're at a particular configuration X, you select an edge at random, for example, this edge, you forget about its status, whether it existed or not. And then your next step in your Markov chain is you either go here, namely the configuration with this edge present, or you go here, namely the configuration without the edge. And the probability of doing this is e to the h of each of these configurations. So math or probability tells you, all of you know this much more than me, you actually use this in practice, these sorts of systems, that if you run this Markov chain for long enough, then you converge to the stationary distribution. So to the distribution that you want, namely this distribution here. And so the basic question is, how long does it take for you to converge? So in 1 minute, I'll tell you the punchline. So someone comes to my office, they posit their models, what sort of graphs are they interested in, or they think is important for their application, their values, beta 0, beta 1, beta 2, etc. So they tell me all of these numbers and these things. So once I get these from them, I should say this is joint work with Alan Sly and Guy Bressler. So what I can do is I can form a function that looks like this. So for example, for the edges and triangles model, this function looks like this. Then from there, I can form a logistic function that looks like this. So this logistic function in the setting that I'm interested in is always going to have one of two forms. Either this line, let's call this line phi of p equals p. So this logistic function over here, this function will intersect this line either at a single point or at multiple points. Okay, and so the final punchline is, if it intersects at a single point, then your Markov chain will mix quickly. So you get close to stationarity in time n squared log n. Whereas if there are multiple intersection points, then it takes you an exponentially long time to run. So this is the basic result that we proved. And just the side effect of the proof is the following. In the regime that you can actually sample from efficiently, it turns out that the math actually tells you that although you can come up with a super complicated model, the actual network that you're simulating from is very close to a model where you have a bunch of n people who connect to each other completely at random. So there was no need to come up with this sort of super complicated model here. There's no reason to come up with a super complicated model. Essentially take a bunch of people and connect them at random according to some probability. So in the regime, so I'll stop over here. The final punchline is, in the regime where you can simulate efficiently, you get essentially a trivial model. And in the regime but in the other regime where you can't simulate, or in the interesting regime where you can get sort of non-trivial behavior, you end up finding that you can't actually simulate from the model. Okay, so that's it. I will stop here.
Okay, thank you very much, Dr. Bhamidi, for a very nice and educating talk. Okay, so we will have time to take a couple of questions. So if you have a question, please just unmute yourself and speak it out loudly. Anybody wants to ask a question? Well, if no, I have a question. I'm just curious for the change point detection part.
Yep.
If you say you assume your gamma is an intermediate sequence, will you lose the dominance of?
Very good question. So maybe I should just add a slide here. So yeah, in interest of time, I didn't mention this, but so what because of what you mentioned, and our findings, what we decided is we also studied a model that we call a Big Bang model. And the basic idea is a change happens way back in time, at the time when the universe originated. That's when a change happens, but then, the network evolves according to some fashion. So one natural model for something like this is between time 0, from time 1 to n, until your system becomes of size n to the gamma. Maybe I should not even use n gamma. Let me just, up to time square root n, your network does one thing. And then from time square root n all the way to n, your network does something else. So f and g. Okay, so this is a natural question. And even in these cases, one can prove various things. In this case, although it may be in this case, although it's obvious, it's surprisingly hard to prove, but one can finally prove that this function the G function wins. It's the function that determines macroscopic averages, like degree distribution, etc., are controlled by this. But this function still controls things like maximum degree. So this function f still controls things like max degree. So the function f can still, in principle, have a huge role on networks, but it has things on extreme value behavior. It affects things, whereas this function g controls things like the degree distribution.
I see. Okay. Okay. And for the seed graph part, how complicated it will be if you say generalize the preferential attachment model to the one which allows you to add edges between two existing nodes?
Very good question. So all of our work is completely in the regime of trees. So this is why I'm putting this slide over here. You know, the centrality measure, right from the outset, depends on the fact that the model I considered is a tree. It's a completely open field in the world of networks. So more broadly, if you have not just trees, but cycles and so on. So if you think about preferential attachment, so if you have, once again, let me just add something here. So if you're dealing with models like f of k of the form k plus alpha, or in fact, even models of the form f of k is equal to k to the alpha, where alpha is between half and 1, then things like maximum degree, these still allow you to reconstruct the seed. Mm-hmm. This is not the case when alpha is between 0 and a half, for example. Then information about the maximum degree might not give you information about where the network actually started from. So we have some results on this, on all of these regimes, but it's a pretty wide open field, extending our stuff to non-tree regimes.
Cool. Okay. Anybody else want to ask a question before you leave? Okay, if no, then let's thank our speaker again. It's a very nice talk. Thank you. I'll see you again on Monday. Bye.
Sounds good. Thank you.